Hello, everyone. Thank you for the introduction. And my talk this morning is about the extracting the most benefit from dietary fiber through in vivo hydrolysis of a functional fiber. My presentation will cover what fiber fraction can be manipulated. I just want you rethink about dietary fiber fraction. I understand that Dr. John Plasky already explained a lot of different concept or different laws of fiber in monogastric animals, and he already summarized how dietary fiber has been classified, and then all the details of that. But I just want to very quickly reintroduce dietary fiber fraction and what fiber fraction are we talking about this morning, and can we manipulate through use of supplemental NSP enzymes. Then I'm going to move on to the extracting the most benefit from the functional fiber fraction, today's main topic. And the content will include accelerating microbial fermentation, increasing energy yield, and competitively reducing protein fermentation, and also increasing mucosal and systemic immunity. Then I'm going to conclude this talk, and then I'm going to move on to the next talk. I just want you rethink about dietary fiber, because as you already heard from the previous speaker, Dr. John Plasky, dietary fiber has four major fractions: lignin, cellulose, hemicellulose, and pectin. In 1850s, there was a method developed called crude fiber. This crude fiber can detect some of the lignin and some fraction of the cellulose, but it never detects whole fraction of dietary fiber, particularly for hemicellulose and pectin. And crude fiber basically represents around 20% of total dietary fiber in most of the cereals. So it's very, very poor predictor, but we are still using it. And we also believe that a lot of study based on the crude fiber still being utilized as a reference to explain the role of fiber in monogastric animal nutrition. But remember that it is only detecting a very small fraction of a fiber, but it doesn't represent the whole fraction of dietary fiber. But in 1960s, Farnsworth and their colleagues developed a new technology or new analytical method called detergent fiber method. And the first thing is active detergent fiber, which is detecting lignin and cellulose, but it never detects cellulose, hemicellulose, and pectin fraction. And there was another method called a neutral detergent fiber. The difference between two methods is only using what sort of medium, acid medium or neutral detergent as a medium. And then this neutral detergent fiber method only detects lignin cellulose and only part of the hemicellulose, and it never detects any fraction of the pectin. And then in 1990s, English developed a new method called non-starch polysaccharide, because this method actually chopping all of this fiber into the single sugars and detecting it apart from the starch. So it called non-starch polysaccharide, detecting whole polysaccharide except polysaccharide from the starch, and it actually can detect cellulose, hemicellulose, and pectin, so whole fraction of the dietary fiber except lignin. So dietary fiber has been defined as non-starch polysaccharide plus lignin. And then if you look at this fraction that non-starch polysaccharide can detect, it actually can detect cellulose, hemicellulose, and pectin. But in monogastric animal nutrition, when you're talking about the functional fiber fraction that we can manipulate during the time frame that digests are staying in the gastrointestinal tract, cellulose often being excluded in the discussion, because it is very difficult to hydrolyze or manipulate the cellulose during the time frame that digests are staying in the gastrointestinal tract for monogastric animals. So nutritionists are now talking about the NCPs, the non-starchy, non-cellulose polysaccharide, which contain which only we are talking about cellulose and pectin. And this is the fraction that we usually call modifiable functional fiber. But if you look at these olden classification of a fiber, crude fiber, NDF, and ADF, we can see that these methods hardly included any of these functional fiber fraction, but we've been discussing about loads of these fiber on monogastric animal nutrition. So we really have to rethink what dietary fiber we have to target to manipulate or make the animal utilize more and extract more benefit from. And it is a functional fiber fraction. It is not the lignin and cellulose, and it is a hemicellulose and pectin that we can manipulate and utilize more and extract more benefit from them. So if you look at this modifiable functional fiber fraction in diet called non-cellulose, non-starchy, non-cellulose polysaccharide, I've been doing this formulation practice with 60% corn and 25% of soybean meal in the diet, with soybean meal, corn with soybean meal, with barley soybean meal based diet. Whatever the combination you formulate your diet, you can see that some of the NCP, non-cellulose polysaccharide, are increasing by using wheat and barley in the diet. But if you look at the proportion of major modifiable functional fiber fraction, it is always rabinogylan, which consists more than 50% of the functional fiber fraction. This is why rabinogylan is the major modifiable functional fiber fraction in any type of monogastric animal diet, and therefore we should target for manipulating the rabinogylan. So by manipulating or make more utilization or increasing fermentation of this functional fiber fraction, what we can extract from the diet. Firstly, we can increase fiber hydrolysis by using NSP enzymes in the diet. That will basically increase nutrient digestion because fiber basically connected to or linked to protein and starch and other component of the nutrient in the grains and in the diet. And also it has a physiological role, as Dr. John Pulaski already summarized in reducing nutrient digestion in the gut. Therefore, by hydrolyzing more fiber, we can basically increase nutrient digestion. And secondly, we can actually produce in vivo very valuable prebiotic fraction, like a xylooligosaccharide, rabinoxylooligosaccharide, etc., by increasing fiber hydrolysis in the small intestine. And these prebiotics are basically increasing fiber fermenting microbiota in the gut, and therefore whole microbiome in the gut improving and becomes more healthier microbial composition. And secondly, by increasing in vivo production of prebiotics, basically we can increase short-chain fatty acid production. And increasing short-chain fatty acid production has a multiple benefit. The first thing is increasing energy extraction because it becomes energy, it's being utilized as an energy source in animal. I'm going to summarize that later again. And then that's the one of the major drivers for energy matrix of NSP enzyme. And secondly, short-chain fatty acids can modulate mucosal and systemic immunity, which is another very important function to increase gut resilience to microbial infection. And finally, it increases resilience to enteric disease, therefore reducing energy partitioning to the immune system. And then this energy that is not partitioned to immune system can be utilized for normal growth of the animal, therefore saving extra energy from the normal physiological process. So I'm going to move on to the how hydrolyzing functional fiber and producing short-chain oligosaccharide can accelerate microbial fiber fermentation. One of the major characteristics you have to check when you are considering use of non-starchy polysaccharide hydrolyzing enzyme for monogastric animals is to look at what is the end product of action of this enzyme that you're gonna include in your diet. Is that enzyme really producing a valuable prebiotics, and that is really a driver for increasing energy value and driver for increasing immunity of the animal. And this is one of the in vitro study we've conducted with our new XYLANASE, COREGEST XYLANASE, and we've conducted to 10 to 180 minute in vitro study looking at the xylo oligosaccharide release from beet-chewed xylan. Beet-chewed xylan is very insoluble xylan source. And you can see that from here, X1 xylose, single xylose, and X2 is xylobiose, xylotriose, xylotetrose, and xylopentose. And these X2 to X5 are very valuable short chain xylo-oligosaccharide that really stimulating fiber fermenting microbial activity in the gastrointestinal tract. So looking at the ability of the enzyme that you have chosen, and then what they can actually produce in vivo by hydrolyzing long chain fiber into small chain prebiotics in the gut is one of the key factor that you have to consider when you're considering non-starch polysaccharide hydrolyzing enzyme. One of the reasons is that because these short chain oligosaccharides basically stimulating microbial cross-feeding mechanism. Firstly, if you look at the three different mechanisms in here for oligofructose, inulin type oligofructose being utilized by bifidobacterial strain and producing lactate and acetate. And this lactate acetate can actually feeding butyrate producing strain to produce butyrate. If you look at the just normal other types of oligofructose, other than inulin, they only stimulating bifidobacterial strain and therefore increasing production of a carbohydrate breakdown product like lactate and acetate. And this lactate and acetate is being utilized by butyrate producing strain, and therefore they are feeding butyrate producing strains. But if you look at this XOS, arabinoxylo oligosaccharide, it is actually giving a multiple cross-feeding mechanism. If you look at in here, arabinoxylo oligosaccharide feeding bifidobacterial strain, and they produce lactate and acetate actually being utilized by butyrating producing strains. So they need this strain to be effectively utilized fiber. And they actually producing ribinose and xylose and butyrate from directly from arabinoxylo oligosaccharide. That actually feeding back to bifidobacterial strain. They actually are cross-feeding each other and growing together. So arabinoxylo oligosaccharide basically are better oligosaccharide prebiotics compared to other types of prebiotics available in the market. And Dr. Pulaski also used this reference, but it actually fit, to explain this cross-feeding mechanism in here. You see that control and antibiotics, xylo-oligosaccharide supplementation basically increased lactobacillus activity and decreased Clostridium and Perisuperbacteria, which is a pathogenic bacterial activity. Therefore, by increasing arabinoxylo oligosaccharide production in vivo by using right source of XYLANASE, you can basically increase or stimulate immunity in the gut, and that really contribute, increasing energy yield, plus making the bacterial population in the gut more healthier and making the gut more resilient to the pathogenic bacterial activity in the gut. Another evidence comes from this Iowa State University study, looking at the high fiber diet with arabinoxylo oligosaccharide and or XYLANASE addition in here. But they actually only added XYLANASE or arabinoxylo oligosaccharide in here. But what enzyme activity they found in ileal digester are amazingly diverse. As you can see in here, even they actually can detect some furanous stage and also all different sort of xylanase and butyrate kinase as well. What this means is these enzymes are not exogenously supplemented enzyme, but by just supplementing xylanase or ribonucleosaccharide, or this xylanase actually producing in vivo ribonucleosaccharide, and these prebiotics being utilized by microbiota and all sorts of different fiber hydrolyzing enzymes are produced by fiber fermenting microbiota. Therefore, by supplementing wide source of prebiotics or creating wide source of prebiotics in the gut, basically increasing whole fiber enzyme activity produced by microbiota in the gut. It is basically accelerating fiber fermenting activity in the gut if you just can create wide source of xylooligosaccharide in the gut by using wide source of enzyme. Moving on to the second benefit, if you're hydrolyzing functional fiber and producing short chain oligosaccharide, basically increasing energy yield in the gut. Everyone knows that by hydrolyzing fiber, basically producing more hexoses and pentoses, going into the microbial system and producing propionate and butyrate and acetate, which is called volatile fatty acid or short chain fatty acid. And if you look at how much volatile fatty acid are produced in the gut, and this is the case of the pig, grower finisher pigs. If you look at the volatile fatty acid production in terms of millimole for 100 gram dry matter intake, you see that in here, basically in the cecum and proximal colon, distal colon, rectum, they producing quite large amount of the volatile fatty acid. And this production is not just a spot on. If you look at the production of these short chain fatty acid in the gut, it actually lasts for 72 hours after the meal. So longer lasting energy source, and it's to keep producing energy. And then if you look at the literature from Serena et al., his colleagues in 2009 estimate that volatile fatty acid 10% of the maintenance energy for when you're feeding low fiber diet, but it can be up to 40% of the maintenance energy for pigs fed high fiber diet. In other study, Lachka et al. In 2021, very recent estimation, estimate that volatile fatty acid account between 20 to 27% of the maintenance energy in the diet containing, in terms of NDF, about 15 to 16% NDF. And this is the NDF level you can find in the grower finisher diet generally. So you can imagine that in general grower finisher diet, about 20 to 27% of the maintenance energy being supplemented by production of volatile fatty acid. It's not a small amount of the energy. So if you can manipulate functional infection and increasing this FA production, then energy contribution from fiber, which are otherwise, unless you not manipulate them, will be excreted to the excreta, will be utilized by the animal and increasing energy extraction from the same sort of feed you're feeding. But it's very well studied that xylooligosaccharide production, increasing short chain fatty acid production, and in this study they studied very well feeding high fiber diet and plus xylanase, and then how much energy is actually increased in terms of digestible energy, metabolizable energy, and that energy content in grower finisher pigs. You can see that by just supplementing xylanase, there was over 150 kcal increase in digestible energy and about 100 kcal increase in net energy content in the same diet. So very valuable if you consider that 100 kcal metabolized energy, if you estimate in your formulation, usually costing around $11 at the moment per metric ton of feed. So very valuable energy source. You can actually increase and extract more from the feed you're actually feeding at the moment. And then this is one of the broader study we conducted in integrated commercial farm in Indonesia. We actually asked them to take out 100 kcal metabolizable energy, or AME, apparent metabolizable energy in broiler diet, but they only take 50 kcal out from the control diet. And then they used multi-NSP enzyme they are currently using, and there was about 2-point reduction in body weight corrected FGR for whole growth initial period. But by adding our COREGEST CYLANASE, and there was about 8.9-point reduction in body weight corrected FGR. And imagine that if you actually applied 100 kcal matrix in here, it could very well maintain the performance with COREGEST CYLANASE, but you could save around $5 to $10 per metric ton of feed. So this is one of the strategies you can actually implement in your formulation by using right source of CYLANASE and applying right amount of the energy matrix. You can actually have a tremendous opportunity to reduce diet cost in daily feed mill operation. And then the next topic, if I'm moving on to the hydrolyzing functional fiber and producing short chain oligosaccharide can competitively reduce protein fermentation, which is very, very important topic. It is important to reduce protein content in the diet to reduce protein fermentation, but also it is important to competitively increasing fiber fermentation and competitively reducing protein fermentation in the gut. So if you can do both, reducing protein and also competitively increasing fiber fermentation, can minimize protein fermentation in the gut. If you look at the fate of undigested nutrients in here, carbohydrate fermentation, basically producing short chain fatty acid and lactate, which are energy source, and also reducing pH, therefore, in the gut, therefore, positively influencing fiber fermenting microbiota. But if you increase the protein fermentation in the gut, basically producing all sorts of different gases with a basic or high pH molecules like ammonia, sulfide, phenol, and amine, etc. And therefore, they increasing pH in the gut, and that is not really good for fiber fermenting microbiota, because fiber fermenting microbiota basically increasing activity at lower pH. And these higher pH are stimulating pathogenic bacterial growth, and also these gases produced by protein fermentation are very toxic and damaging mucosal layer in the gut, and therefore, in general, increasing energy costs for animals. So the problem is they are all microbial activity, and they are very competitive. So if you maximize the carbohydrate fermentation, you can competitively minimize protein fermentation. And this is one of the strategies you can actually take by using non-starch polysaccharide hydrolyzing enzyme. If you look at in this mechanism, how protein fermentation byproduct can damage the gut, particularly the ammonia is a very well-known toxic component, and it's been reported that ammonia dose-dependently inhibit mitochondrial respiration, and particularly non-ionized ammonia can freely pass mitochondrial cell wall, and therefore block ATP production in the mitochondria. And if they cannot produce ATP in the mitochondria, what happens? The cell dies. And therefore, it causes mucosal damage. And once mucosal damage, then you know that all the antigens and pathogens are coming through there. And then animal responding to immunity, and animals start using protein and energy for responding to the inflated immune function. Therefore, they decrease production. And then moving on to the next topic, hydrolyzing functional fiber and producing short-chain oligosaccharide can increase mucosal and systemic immunity. This is a very new concept and very well studied recently. I just want to share this new idea to you. short-chain fatty acid is known to shape mucosal immunity, particularly if you produce the short-chain fatty acid more in the gut by stimulating microbial activity. They can actually involve in naive T cell development to regulatory T cells and increasing energy source, like butyrate is being energy source for enterocytes in the gut. They also stimulate T regulatory cell and involved in differentiation of the regulatory T cells and involved in anti-inflammatory cytokine production, such as interleukin 10. And they also interact with dendritic cells and macrophages, and therefore increasing anti-inflammatory cytokine and decreasing pro-inflammatory cytokine production. And they also involved in goblet cell numbers and mucin production as well. And then they also involved in neutrophil chemotaxis production in the gut. So all these immunity or gut-associated immune function basically shaped by microbial activity and microbial byproducts such as short-chain fatty acid. And recent study also showed that hydrolyzing dietary fiber and producing short-chain fatty acid are increasing immunoglobulin A production in mucosal layer in here, and also involved in immunoglobulin G production in systemic cells such as the spleen. So short-chain fatty acid is not just an energy source for animal, it is shaping immunity of the animal, not only in the systemic, not only in the mucosal level, but also in the systemic level as well. And again, if you look at more deeply how short-chain fatty acid can play a pivotal role in preventing bacterial pathogenesis in the gut. Generally in the gut, there's a very low oxygen level is maintained. This low oxygen in the luminal environment inhibit expression of a virulence factor of the pathogenic bacteria such as E. coli in here. So you can see the red in here, the virulence factor expression is suppressed because there's a low oxygen in the gut. But as they are moving on to close to the gut, what happens then? They can actually sense environmental oxygen that is expelled from the cell into the environment. And they have a sensor called FNR. And if they sense oxygen, if there's an increasing oxygen release in the gut, what happens is they are sensing it and they deactivate this sensor, FNR, and they start expressing virulence factor of this pathogenic bacteria. So these bacteria are non-pathogenic and lower oxygen level and becomes pathogenic when there was an increasing oxygen excretion from the cell. And this increasing oxygen excretion is happening when there's a lower level of fiber fermentation. If you look at in here, in healthy colon situation, butyrate is produced by microbiota from the carbohydrate fiber fraction, and this butyrate is going into the epithelium, this enterocyte. Within the enterocyte, this butyrate is being utilized to produce ATP. During this process, they are utilizing oxygen that is delivered from the blood vessel into the cell. So there's no oxygen expel or oxygen excretion from the cell in the normal healthy condition with general fiber fermentation situation. But what happens when you kill these good bacteria by using antibiotics? And there's no fiber fermenting microbiota, therefore butyrate production is reduced, and there's no energy sources for enterocytes in here. And then what happens is they start using glucose from the blood to produce ATP, but unfortunately, conversion of glucose to ATP, they are not requiring oxygen. So this extra oxygen now in the cell, how they actually doing it? They actually excrete it into the gut. And this oxygen actually stimulating this virulence factor of this pathogenic bacteria, and this pathogenic bacteria start growing and becomes very aggressive and attack animals. And it happens when you actually have, Salmonella or E. coli or whatever the pathogenic bacteria, once they start, feeling that there was a lower energy level coming into the enterocyte, they start using glucose and they actually expel oxygen in here, and this oxygen stimulating this pathogenic bacterial growth, and they becomes more virulent and they becomes more aggressive, and therefore animal get infected. So short chain fatty acid is not just an energy source; it plays a pivotal role in preventing bacterial pathogenesis in monogastric animals. And in sound nutrition, if you have good dietary fiber and good dietary fiber fermentation and producing short chain fatty acid, and this dietary fiber are actually changing microbial composition, and this microbial composition actually interact with the immune system of the gut. And this information, bacterial information, all goes to mammary gland, and this mammary gland contains all this genetic information plus, milk fat that was basically, affected by volatile fatty acid going into the mammary gland, and also pro-inflammatory cytokine and milk bacteria, all affected by this bacterial composition, and therefore shape, affect this progeny health in the commercial farm. So let's think fiber as not just an anti-nutrient, it's a very, very valuable fraction if you can actually utilize it, modify it and utilize it widely. It is a golden fraction for monogastric animal production. We conducted one study at North Carolina State University in US using our COREGEST XYLANASE in wiener pigs. We basically fed a control diet, and with control diet with COREGEST XYLANASE. And then we collected jejunum tissue samples and measured these immune parameters and antioxidant parameters in there. What we found in here, as you can see in here, control plus COREGEST XYLANASE in expresses of pink compared to control in sky blue. What we found in here, there was a significant reduction in TNF-alpha production. And there was a reasonable increase in immunoglobulin A, and also there was a significant reduction in malondialdehyde, which is an indicator of oxidation stress in the gut. So how this happened? If you consider the XYLANASE increase xylo oligosaccharide production in the gut, and that increases xylo oligosaccharide fermentation by commensal microbiota in the gut, and that produces short chain fatty acid. During this process, we increase the nutrient digestion and we increase the healthy microbial composition. Therefore, we petition the less energy to the immune system, as you can see in here. And also by producing more short chain fatty acid, we increase the energy contribution from the same diet, but also increase the mucosal and systemic immunity, as you can see in here. By doing so, what we found in the performance, you see that there was a significant increase in growth performance of these animals. So multiple layer of mechanisms actually involved in how XYLANASE can actually improve performance of the animal. It basically improves not only the nutrient digestion, but also involved in healthier microbial community, and also increasing immunity of the gut, therefore reducing the energy going into the immune system that contributing back to the growth of the animal is the whole picture of utilizing functional fiber fraction in the gut. That's all my talk. If I conclude, traditional estimation of a fiber do not represent functional fiber fraction that can be manipulated. Monogastric animal feed contains 85 to 120 kilos of functional fiber for metric ton of feed, which is a huge amount of the functional fraction. We've been thought that it's the useless fraction and anti-nutritional factors, but it contains about half of the very, very valuable functional fiber in there, which you can actually manipulate if you widely select NSP hydrolyzing enzyme. XYLANASE can hydrolyze the functional fiber fraction and produce short-chain fatty acid, short-chain xylopolysaccharide, and therefore we can actually extract most benefit from the partial hydrolysis of functional fiber using XYLANASE. Particularly, it can accelerate microbial fermentation, and therefore we can make healthier microbial composition in the gut. And we also can increase energy yield and reduce diet costs, and therefore improve animal performance. And also we can competitively reduce protein fermentation, which is producing very harmful gases in the gut. Therefore, we can actually minimize mucosal damage, and we can also increase mucosal and systemic immunity, therefore decreasing energy partitioning to the immune system, which will be used for growth of the animal. So that's all for my presentation, and I hope I can actually entertain your question in the later session. Thank you very much.
Grow and Act.